So we return to the domain of predominance. We did the analogy between acid, base, and complex, and the characteristic in the acid is Ka, the characteristic in the acid base is Ka, the characteristic in the complex is Kd. In the acid base, we have a couple HAA minus, and the presence of the species depend on the pH of the solution. And we proved if pH is less than pKa minus 1, so the acid predominates, which is the donor. And if pH is greater than pKa plus 1, the base predominates, which is the acceptor. By the same way, suppose we have PL equal pKd plus log m divided by ml. This relation can be applied in the exercise independent of the exercise. Since this relation is deduced from Kf, and Kf is a constant of the complex given, so you can apply PL equal pKd plus log m divided by ml, but pay attention that these concentrations should be the concentrations at equilibrium of the complexation. So, if m is greater 10 times ml, so m is predominant on ml. So in this case, m over ml is greater than 10. So log 10 equal 1. So PL is greater than PKD plus 1. So if PL is greater than PKD plus 1, the M predominate. Okay, this is on the scale of PL, the M predominate. What is M? M is the acceptor. In case of the base, acid base, when pH is greater than pKa plus 1, the base predominate, which is the acceptor. So look, we have the same analogy with the acid base. If ml is greater 10 times than m, so ml predominates, and in this case, the PL should be less than pKd minus 1. In the acid base, when the pH is less than pKa minus 1, the acid predominate. In the complex, when PL is less than pKd minus 1, the complex predominate. The complex is donor. The acid is donor. So, if a student forget the domain of predominance of the complex, what to do? Is to write the domain of predominance of acid base. This is pKa, pKa minus 1, pKa plus 1. Here we have the base, pKa minus 1, we have the acid. So I will do the same analogy. I make a scale of P. P of the particle exchange in the acid base is pH. Here, suppose PL. The characteristic in the acid base is pKa. The characteristic in the complex is pKd. So pKd minus 1 and pKd plus 1. If pH is less than pKa minus 1, so if PL is less than pKd minus 1, the acid predominate. The acid is donor, so the donor is ml. And here we have m. So on the scale of PL, when PL is less than pKd minus 1, so the complex predominate. And if PL is greater than pKd plus 1, the m predominate. On the scale of PM, if the PM is less than pKd minus 1, the complex predominate. And if PM is greater than pKd plus 1, the other acceptor predominate, which is L. So this is the same analogy of the domain of predominance acid base. So in pH, acid is donor pH. If you want to work on scale p particle exchange Pl, so the donor is the acid, the donor is Ml. On scale Pm, the donor of the acid, the donor is Ml. On the scale of Pl, the acceptor on the scale of the acid base is the base, which is acceptor. On the scale of Pl, the acceptor is M. On the scale of Pm, the acceptor is N. So we obtain the same analogy. Predominance of successive complexes. Suppose we add Cu plus NH3. So by theory, we can have formation of 4 complexes, CuNH3 2 plus, CuNH3 2 2 plus, CuNH3 3 2 plus, and CuNH3 4 2 plus. The first is characterized by Kf1 or beta 1. The second is characterized by Kf2 or beta 2. The third by Kf3 or beta 3. The fourth by Kf4 or beta 4. We do the same analogy for the polyacid. For the polyacid, we have pH, we have pKa1 and pKa2. Suppose we have H2A, HA minus, and A2 minus. Do the same analogy for the complexes. Suppose pH, you want to work on the particle exchange, which is also on Pl. pK, so pKd and pKd. We have to look to the value of pKd, okay? Which is pKd1 or pKd2. Okay, H2A, you have Ml2, Ml, and you have M. So this is pKd2. Since Ml is Kf1 or Kd1. Okay, then Ml2 is Kf2 or Kd2. So this is pKd2 and this is pKd1. Okay. Ml is Kf1, yes. This is Ml, so pKd1. And this is Ml and Ml2. So we have the same analogy. We have the same analogy with the acid base. Suppose I have Ml3. Look, pKd1, pKa1. So here we have pKd3, pKd2, pKd1 on the scale of Pl. On the scale of Pm, we have pKd3, pKd2, pKd1, but pay attention, on the scale of Pl, you have M, on the scale of Pm, you have L. If the student forget the domain of predominance of successive complexes, the easiest method is to write the domain of predominance for the polyacid. Then, from this domain of predominance, from the ladder diagram of the polyacid, you can deduce the ladder diagram for the successive complexes. We pass now to the reaction of complexation. First, In the acid base, we wrote acid plus acid, no reaction. Base plus acid, no reaction. Base plus base, no reaction. So acid plus acid, no reaction. Base plus base, no reaction. Acid plus base, necessary we have a reaction. But this reaction may be limited, may be advanced, may be quantitative, and may be complete. It depends on K of the reaction. In the oxidation reduction reactions, we also write Ox plus Ox, no reaction. Red plus red, no reaction. Ox plus red, necessary we have a reaction. And this reaction might be limited, advanced, complete, quantitative. It depends on K of the reaction. In the solubility, we also explained that Ag plus Fe3 plus, no reaction. Cl minus plus NO3 minus, no reaction. But Ag plus Cl minus, we can have a reaction if we have a KSP given of AgCl. That means we have the possibility of precipitation of AgCl. We pass to the complex. M plus M prime metal ion plus another metal ion, no reaction. Metal, a ligand plus another ligand, no reaction. M plus L, metal plus ligand, implies reaction if Kf or Kd of Ml is given. That means you have formation of complex. And this reaction of complexation might be limited, advanced, quantitative, or complete. It depends on K of the reaction. So this is the reaction of complexation. We have a reaction of complexation when we add a ligand to a metallic ion and should be given the Kf or Kd of the complex fold. This is the reaction of complexation. Suppose I have a complex plus M prime, which is a metallic ion. In this case, the complex is donor. The M prime is acceptor. So I can have donor acceptor reaction to give Ml prime plus M. So what happens in this reaction? The Ml release its ligand to M prime. So M prime capture the ligand from L to give M prime L. And when Ml release the ligand, so Ml become M. So what are the couples involved? The couples involved are Ml, L, and M prime, L, M prime. Pay attention that this reaction is different from the below reaction. M plus L is a reaction of complexation of M by L. This reaction, Ml plus M prime, is a reaction that exchange a ligand between two metallic ion M and M prime. So Ml will release its ligand to M prime. So we obtain a new complex M prime L plus the initial metallic M. So this reaction is called exchange reaction between two metallic ions. The below reaction is a reaction of complexation. According to the thermodynamics that we studied in the first semester, this reaction is favored in direction 1 if M prime L is more stable than ML. According to the thermodynamics, this reaction is favored from left to right, or in direction 1, or in the forward direction, if M prime L is more stable than ML. What is the meaning of ML prime is more stable than ML? That means if Kf of ML is greater than Kf of M prime L is greater than Kf of ML. Or if Kd of M prime L is less than Kd of ML. So in some examples, they give the reaction of exchange between two metallic ions, and they ask, is this reaction favored in direction 1 or in direction 2? So what to do? I have to say that the reaction is favored in direction 1 in the forward if M prime L is more stable than ML, is favored in direction 2 if ML is more stable than M prime L. So I have to compare the stability of ML and M prime L according to their values of Kf. So what is the equilibrium constant for this reaction? K of the reaction. Why I should write or I should calculate K? In order to know if this reaction is limited or advanced or complete or quantitative. So K of the reaction is equal to the concentrations of the product is equal to the concentration of the complex 1, M prime L times M, divided by ML and M prime, and pay attention, the concentrations are at equilibrium. So Kr equal M prime L divided by M times M divided by ML M prime. I don't have Kr. I should deduce Kr given only Kf and Kf prime. So I should transform Kr to Kf and Kf prime. I multiply by the ligand L in the solution and ligand L on the solution. So M times L divided by ML is Kf, and is 1 over Kf. Don't forget that Kf of ML equal ML divided by M times L. So this is 1 over Kf. M prime L. This is Kf prime. So K of the reaction is equal to K prime F divided by Kf, or equal Kd divided by K prime D. Okay? Then according to the value of K, if K is very high, I can know that the reaction is favored in direction 1. If K is low, I can say that the reaction is favored in direction 2. And according to the value of K, I will determine the types of calculation. If the reaction is complete, I will work at T equal infinity. If the reaction is incomplete, I will work at the time of equilibrium. So in the complexation, we have two types of the reactions. The type 1 is between M itself and L. The type 2, this is a reaction of complexation. We can have another type of reaction, which is the exchange of the ligand between two metallic M, or the exchange of metallic M between two ligands. This is the exchange of ligand between two metallic M. I can have another reaction. So M plus L give ML. ML plus M prime give M prime L plus M. Or I can have ML plus L prime that give ML prime plus L. So the first is a reaction of complexation between M and L. The second is the reaction of exchange of ligand between two metallic M. The third is the exchange of metallic M between two ligands. So we have three types of reactions in the complexation. What type should I use? It depends on the exercise. In some exercises, he said you have reaction M plus L. In other exercise, he said you have ligand L prime added to ML. So this is exchange of ligand. Okay. And in the third type, you have ML, you add M prime. This is exchange of M prime, or exchange of ligand between two metallic M. So it depends on the exercise. Direction of the complexation reaction. How do I know the nature of the complexation reaction? I will do the analogy with the acid-base. To predict the direction of the acid-base reaction, we make a scale, increasing scale of pKa, increasing scale of pKa. On the left, we put the base. On the right, we put the acid. So the base is acceptor, the acid is the donor. In the complexation reaction, instead of pKa, we make a scale of pKd. On the left, we put the acceptor. Suppose the acceptor is the metal M prime and M. And on the right, we put the donor, which is the complex M prime L and ML. So look to this relation. If you add M prime plus ML, you have advanced reaction since it's in the direction of gamma. If you had M prime L plus M, you have reaction, but this reaction is limited since it's in the anti-gamma reaction. So to determine the direction of a complexation reaction, it's necessary to review the species present, write the balance reaction, calculate the equilibrium constant, consider the reaction in ascending order of their constant. The concept of predominant reaction is still valid. Note, the use of predominance diagrams is always wise for predicting reactions and testing the data. So this is the same analogy of the acid base, but instead of pKa, we put pKd. Instead of the base of the acceptor, we put M. In some exercises, the species are not M. We can do pKd. The other ligand acceptor is L prime, M prime L, the couple. So L, ML. This is acceptor donor. This is acceptor donor, and this is acceptor donor. So we can work on other scale. It depends. You have to work on this scale or on the second scale. It depends on the nature of the exercise. In the first, we have exchange of ligand between metallic ion. M prime plus ML exchange the ligand. In the second, we have exchange of M between two ligands, L prime and L. So it depends on the type of the exercise. Look to this scale. L prime will react with ML and the reaction is advanced since it's in the direction gamma. If you mix M prime L M prime L with L, no, this is ML prime. This is ML prime. And in the second, we have L, this is ML. Okay, so the reaction between L prime and ML is advanced since it's in the direction of gamma. The reaction between ML prime and L is limited since it's in the direction anti-gamma.